So I'm truly honored to accept this professorship at TERI University, the UNESCO professorship, and I think this is my first lecture series. And as was said, my expertise is in climate science and with a focus on atmospheric sciences. There are many reasons for giving such a lecture series, but I have one more I want to add to that is, as we know, climate change is probably the most important problem society is going to face in the near future. And particularly those under 40, I hope many of you are attending in that age group, it's going to be the most serious and important problem you'll be facing. Not 50 years from now, not 100 years from now, but 10, 20 years from now. And as you all know, in spite of its importance, for varieties of reasons, our global leaders have either failed or unable to act on it. There's tremendous amount of scientific background and knowledge on why we should act on it. So it turns out, looking at this, I've been working in this field for at least 40 years and watched with frustration how the science has not been effective. So about 5 years ago, I developed an approach of mitigating climate change, making a huge dent by slowing down the warming. And that approach, which I'll come to in the third of this series, requires bottom-up action from individuals, social entrepreneurs, foundations, NGOs, etc. It does not necessarily require 160 nations to agree on something. So what better way to communicate that other than such a seminar series? So I'll start with my first slide. No, this is not the first one. Right. So if you can, yeah. So as Dr. Kamna, who has been coordinating this, there are 3 parts, about 45 minutes each. The first one is science of climate change. And I just wanted to give you a brief background before I dive into the actual details. The climate change areas become quite political. And many of the results which you get to see in the media are from models. And as you know, we still haven't figured out how to model the planet Earth in all its complexities. But it turns out that there is a parallel approach of relying on observations. See, I was trained in India as an experimentalist. So I don't believe anything unless I can observe it, see it, measure it, observe it. So I'm going to walk you through that approach. So I set up observations around the planet. I have over 5 or 6 stations as we speak now. Then I design satellite experiments. Then I conduct field experiments where we take ships, aircraft, and balloons. My latest toy is using unmanned aircraft. This has become a powerful tool for making measurements in the atmosphere, and you'll see the next one. So these are, about 2 meters, wingtip to wingtip. We pack them with the instruments and fly them in stacked formation so we can observe the atmosphere in the most excruciating detail. So nothing escapes our attention, and it's packed with all kinds of instruments. So let me then go on. So what are the sources of pollution we are concerned about in terms of climate change? The first is, of course, industries, smokestacks. Next is burning of fuel in our transportation sector, open burning of forests, biomass burning, agriculture. That, by the way, is the village where I come from in South India. It's adjacent to a major city called Kumbakonam. And then that's my grandmother's kitchen, where I used to visit. Very excellent summers. So let's ask ourselves the question, why should my grandmother, she's not alive now, unfortunately, just let's pretend, why should someone now who is sitting in this village home worry about what car I'm driving? Likewise, someone sitting in the US, why should they worry about biomass burning tens of thousands of kilometers away? Watch a close look at the next movie, which shows how fast air carries pollutants around. This one is really showing water vapor, but it applies to pollutants too. So the clock is sitting on the, ticking at the bottom. This is what's called now a national climate model. I helped build the first version of it 20 years ago. So you can see air from China, within a matter of 4 to 5 days, travels across the vast Pacific, reaches US, carrying all the pollutants. I'm sitting here in California, so when we receive this gift from China, we send our gifts, our pollution, in less than 2-3 days to Europeans, and the Europeans ship their pollutants across, and world goes round. And you can see how biomass burning, other pollutants from Africa, dives into the Antarctic within a matter of 2-3 days. So the moral of the story is everyone on this planet is on someone else's backyard. So we are not going to solve this problem by pointing fingers at somebody else. Okay? So what happens then, gases we put out, carbon dioxide is a major thing. So let's take a 30-second lecture on what is carbon dioxide. Anything which burns has hydrocarbons, carbon and hydrogen. So when you burn it, the carbon is released, it combines with oxygen and becomes carbon dioxide. Okay? This carbon dioxide, once you release, for example, let's say you took a bus, 50% of what came out of your tailpipe, the gas carbon dioxide, stays in the air 100 years from now. About 20% stays for 1,000 years. So it doesn't go away. So it's not surprising that carbon dioxide has steadily increased. This is called this Keeling curve. Dave Keeling has become an icon now, and he was my colleague. In fact, he was the first scientist who welcomed me when I joined Scripps Institution of Oceanography 23 years ago. I'm just an amazing person to interact with. So this blanket is thickening. Okay, now I think the metaphor I want to carry you is that the greenhouse gases act like a blanket. You emit it locally because of transport, it goes around the planet very quickly. And remember, it's accumulating. So if you want to know how thick is that blanket we have put up, it's about 1,000 billion tons. Okay? So what is 1,000 billion tons is equal to 500 billion, say Toyota Corollas circling around the planet. Just imagine the weight of this blanket. Okay? That's how much pollutant we have put in the air. So now let's find out, why should we worry about what this blanket does to something like the monsoon, the Himalayan glaciers, Arctic sea ice? What is the connection between these gases and climate change? Just to give you a perspective, this concentration I showed you the last 50 years, and you go back in time from ice core, we can know how to measure the CO2. It was only about 280 in this unit. ppm is parts per million. 1 part of CO2 per million parts of air molecules. So just how tiny that is. Okay? And you can see that increase started something roughly about 1800. Since the dawn of the Industrial Revolution, James Watt, invented the steam engine and started the industrial age, and we started releasing fossil fuels. So just one more background. I'm assuming many of you attending, this is the first time you hear something about atmospheric science. So let me just talk about this thing called troposphere, okay? That's going from the surface to about 50, 80 kilometers. The first 10 to 15 kilometers is what we call troposphere. This is where temperature decreases with altitude. That is why when you go higher altitudes into the mountains, it gets colder, not because the mountain is making you cold, the air temperature decreases with altitude, okay? So that is where most of our weather happens. So we call that troposphere, the region above is stratosphere. So now let's talk about, I've hopefully convinced you that gases in the air, once you put them as pollutants, particularly the long-lived gases, carbon dioxide, surrounds the planet like a blanket. So why should we worry about this blanket? So let's now take a quick 1-minute lesson. I'm condensing my whole graduate course into this one slide, okay, on climate. The fundamental energy source for the planet is sunlight, solar energy, that drives everything. Not all of that is absorbed by the planet, about 28% is reflected. So I'm not going to use much jargon, but I want you to remember this jargon, albedo. Albedo is the percent of energy reflected back to space. 28%. This is what I spent the first 5 years of my life in the US designing a satellite experiment with NASA to measure the albedo of the planet. So we know that pretty precisely. So then 72% goes and heats the surface and the air. And what happens? There has to be a balance. So the surface of the planet gives off this energy, as we call it, heat energy, infrared energy, so on and so forth. So this process of what comes in as sunlight, visible radiation, leaves the planet as infrared. Until the two are in balance, we call it Earth energy balance. Okay? And the planet has been sailing merrily on this energy balance for millions of years. And then we come in with our fossil fuels and put this blanket. So let's ask yourself, how does a blanket keep you warm on a cold winter night? Not because the blanket is giving any heat to you, it traps the body heat, right? It prevents you from losing heat from your body. That's exactly how this greenhouse blanket behaves. It lets in sunlight, but it traps the heat coming from the earth and keeps the earth warmer. Okay? Until 1970s, we used to think carbon dioxide is the only way we are upsetting the planet's climate. I was not trained in India as a climate scientist. I was an engineer. I go to the US, learn about this. Then I said, how about chlorofluorocarbons? Because I worked in a refrigeration industry in Hyderabad. It used to be called Shriram Refrigeration Industry. My job was to look at this chlorofluorocarbons, so I got curious. So I was surprised in 75, I came with this conclusion in this paper that addition of one molecule of CFC traps more heat than adding 10,000 molecules of carbon dioxide. So these CFCs are used as refrigerants and it escapes ultimately. So here it is, this is a synthetic molecule. We have invented a molecule 10,000 times more efficient in trapping heat, a super greenhouse molecule. That sort of opened a Pandora's box, and other groups pointed out other molecules. And so we estimated how much heat is trapped by this blanket, okay? But I was curious. Remember I said I don't trust anything like calculate or use models. So as a postdoc, I teamed up with a remarkable engineer at NASA. We designed the satellite radiation budget experiment. We had a telescope which will scan the Earth, and we had a solar radiometer which will measure how much is coming in and how much is leaving. So from that, we put this picture together, okay? Remember I talked about the blanket. Nature gave us a blanket, okay? Otherwise, this planet would be frozen like Mars. none of us would be even here. There won't be any TERI University without this greenhouse blanket, which nature gave us. That's mainly water vapor. So I wanted to understand, before we figure out what we are doing to the planet, we need to figure out how thick is that blanket. I'm not going to go through all the units, but the normally units we use in climate science is watts per square meter. Watt is the same energy. You say a 60-watt light bulb, it's the same thing. That per square meter is per square meter of the Earth's surface. So that is the energy, about 400 the Earth is giving out, and we found out 1/3 of it is trapped by this blanket Mother Nature gave us. Okay? That is why this planet is so warm. And the addition we have put is about 3 watts. For those of you who call the whole climate science a speculative, it's just controversy by scientists to stop industries, etc., etc., that number, that how thick the planet's blanket has become and how much additional heat is trapped, comes from basic quantum mechanics. Okay? That's what I learned in the US when I left here after my graduate studies to do PhD, quantum mechanics. It's basic quantum mechanics and basic measurements. That number, we know that within 25%. So there's no escaping that 3 watts. So if you compare that with this, we have made the blanket thicker by about 2.5%. Okay? So remember, sunlight coming in, heating the planet, and the planet gives off this heat as infrared, and about a third of that heat is trapped by the blanket Mother Nature gave us, and we have made the blanket thicker by about 2.5%. So fundamental laws of physics tell you the planet should get warmer. I have to tell you, at least there are 5 to 10% skeptics, even among scientists. I'm not talking about the skeptics politically motivated. I'm talking about scientists. Because in science, remember, we don't agree on. We all argue. Even the most skeptic scientists concede the planet would heat up. What we are arguing about is how large and how soon. Okay? That is where the argument is. It is absolutely incorrect, ridiculous, and flawed to say this gas is not going to warm the planet. Everyone knows it's going to heat up. The argument is in how large and how soon. That's what I'm going to talk to you next. So we have trapped 3 watts, and the outside world thinks it's all from carbon dioxide. Only 55% is carbon dioxide. That was my work to pin it down. The other 45% is coming from gases other than carbon dioxide. That is where my solution lies in. I'm going to bring it up. Okay? So please keep that in mind. So this number we know, like I said, within about 25%. So I just want to give you another reference point. I said the blanket has become thicker. In the literature, it's called radiative forcing. I mean, if you want to follow the scientific literature, fine, but think of it as heat trapped, additional heat trapped by the blanket. What does this 3 watts really mean? It's equivalent to, went the wrong way. It's equivalent to burning a 60-watt light bulb for every 20 square meter. I use this because I think that is the typical size of an undergraduate student's dormitory room, where 2 people, at least those days, when I was in India, maybe now you're all enjoying much better dorm accommodations. So how many such bedrooms are there in the planet, right? When you do that, it's 25 trillion. A trillion is 1,000 billion, 60-watt bulbs, distributed around the globe, burning all the time, day and night, throughout the year. That number we know within 20%. Just imagine the volume and the massive amount of that heat, and to think that it's not going to warm the planet, again, belies all laws of physics. So there's one problem. I have to add one complexity here. So imagine now, okay, again, go back to the bedroom, put the blanket on top, and you've been having the blanket, now you made it thicker. You added another blanket. You're going to get warm, So when you say you, that is the oceans and the land. What happens when you heat the oceans? Just go back, do the simple experiment. Remember, I keep reminding you, unless I can experiment with it, I don't believe what I hear from models. Okay? So if you put a burner and put a water in a beaker, if you wait long enough, that water will be gone. Right? Evaporate. Why does it evaporate? The vapor pressure of water depends on temperature. So what happens to that water when it goes up? It stays in the air. But remember, I told you water vapor is the dominant greenhouse gas. That's what traps 1/3. What we have added is 2.5%. So then you put this thin blanket on top of you, that is the 1,000 billion ton CO2 and other gases, and it heats your body, and you start evaporating moisture. Think of it, you're starting to sweat. That blanket gets even more thicker from the water vapor. Water vapor traps even more heat, and it amplifies this. In the scientific jargon, we call it positive feedback. But don't get confused. Positive means it gives the impression it's good. So we have not changed it to call it amplifier. So that vicious cycle goes on, right? You heat the thing with the greenhouse gases, it starts evaporating moisture, and that moisture is a greenhouse gas that warms and keeps going. Is there evidence for this? Absolutely. If you look at the water vapor density in the air, take a water vapor instrument from the equator or the pole and travel straight to India, you see the humidity increasing by a factor of 25 to 50. It's a well-known fact. Okay? And it's the same reason, particularly in the northern latitudes here, winter is dry and summer is humid. Right? You need all kinds of, if you have a dry skin like me, you need a lot of cream in the winter. Why? Because the humidity drops and your body is evaporating moisture. So it's a well-known fact. You can't escape it. And the water vapor spectroscopy is what we understand much better. So for those of you physicists among you, I'm not going to describe this. This is an equation called Clausius-Clapeyron equation, have been derived ages ago by physicists. Okay? And what it shows, you differentiate that. It tells you for each degree warming, water vapor in concentration in the air would increase 6 to 10%. This was what was tested by an undergraduate student of mine at the University of Chicago, Amit Raval. He became well known. This paper went to Nature, New York Times covered it. Unfortunately, it went to his head and he stopped doing research after this. But that is inescapable. Why is that important, 6 to 10%? You see, India and the planet has warmed by about 0.8 of a degree. That means the water vapor over the whole tropics has gone up by about 6 to 10% just in the last 40 years. Okay? And that is trapping even more. There is one more amplifier, and then I'll move on, is that what happens to snow and ice when you heat? Remember, when you take the ice cream out of your refrigerator, it melts, right? Why is that a problem? Snow and ice is white. What does white mean? It reflects most of the sunlight. Fresh snow reflects about 85% of the sunlight. So what happens? You remove the snow, underlying ocean. You've seen the ocean, it's dark, right? It's blue. So you go from 75% reflecting sunlight to 8%. It's a huge addition of sunlight. So we know our glaciers are melting, sea ice is melting, so that feedback goes on. It also amplifies. One of my students, Christina Pistone, I think she may join us, she's, for a thesis, one of the first to make measurements of how much energy is being pumped back into the system. Observationally. It's been known from models, now we know it from observations. So I think this is one example of that. This came from my Austrian colleague, Heberle, and he shows in 1985, it's in Alps, 75% of the mass in the Alps is gone. Snow firn, and then when it melts, and then by 2003, the albedo goes from white to dark. Okay, so these are all empirical facts, and this is Pistoni's work, which shows just in the last, you look at 2 periods, there's warming, and the sea ice has melted. So these are all empirically known. It's not really, you see here, I'm not using any model results. If you look at media and look at more reports, it will all be model results. And that is one of the reasons this field has become controversial. People think, oh, models, I can't trust them. So, just want to quickly, what were the predictions? Any scientific theory is judged by the predictions it made. These are not predictions so-called after the fact, before. So I had teamed up with the meteorologist Roland Madden and forecasted in 1980 that if our theory is right, the warming will be seen by 2000. And so on and so forth. The water vapor feedback was predicted in the 1960s. The polar region will be amplified because of the feedback. The stratosphere will cool, sea level rise, etc. All of this have been shown to be happening except the last one. And I'll talk to you about that. Okay? That the global average rainfall should increase. So that was a paper in 1980. I just want to read you the last sentence from their summary. Further consideration of the uncertainties in model predictions on the likely delays introduced by ocean, the detection of warming, if it occurs, should happen before the year 2000. So we in fact gave a definite period. So now let's look at the observed data. This is temperature records around the planet, global mean, surface temperatures, starting from 1850s. Before that, we don't have good records, until about 2005. And you see this has been ups and downs. In the last 50 years, it has risen. If you think of it as background noise, it's in year 2000, it clearly came about the background noise. Okay? And the IPCC confirmed that. The second one is that another prediction, not by me, by other, this time, scientists, is that if the global warming theory, if just the land warmed, that doesn't confirm the theory at all. The whole planet should warm. And that was spectacularly confirmed. My institution, Scripps Institution, played a huge role, sending buoys and drifters to the ocean. And it is showing the ocean heat content, or think of it as a warming rate, has been steadily increasing. So land is warming, and the ocean up to depth of 1,000 meters is warming. Okay? This is the sea ice. And they're using satellite data starting from 1960, the sea ice has been retreating almost about 25%. So these are all things happening. The planet is changing. It is not the planet you inherited when you were born. Even if you're 30 years old, you are here. Since then, things have gone down. This is the Arctic warming, NASA satellite data, and over the last 30 years, okay? And that has warmed by more than 2 degrees. Huge warming in there. This amplification was forecast again. And this, I'm not going to go through this, but it's for those of you, I'm hoping this thing is record. Many aspects. Sea level rise, I'm going to talk to you about later. All of this, the snow cover is decreasing, and the stratosphere should cool. We predict, you can see the humidity. See, that is the key. If the humidity didn't increase, it will be a fatal blow, the theory. Okay? But unfortunately, it is increasing. Now let's come to the precipitation. This is where our predictions were not really seen, okay? Particularly in the tropics. This is the warming trend we showed the last 52 years. Last 50 years. The reason I picked the last 50 is that that's when the warming has been rapid. You see the red regions is where the precipitation is decreased. Major proportion, the well-known Sahelian drought, millions in sub-Saharan Africa perished and suffered. And if you look at the India, see clearly in the Indo-Gangetic plains and going on to Burma and this, rainfall has decreased. The major thing also is in China, there's been a shift. Southern China is getting flooded with more rain, northern China is drying out. And in fact, that comes later, okay? This cannot be explained from greenhouse warming, at least not all of it, okay? So we're trying to figure out what's going on. I have my own work that it's from particulate pollution. In fact, tomorrow, TERI University is assembling experts from this region, IITs, other universities, to see if we can look into this problem. All right, so now let me go on to the next, So I don't want to go into the details here, but just to back up how I came to that deduction. The greenhouse gases so far have added 3 watts per meter squared. And if you look at our climate theories, now I'm using models, okay? Because I'm talking about the future. What we conclude is that we have already dumped enough gases on the planet to heat it by 2.5 degrees. I'm just rounding off. And I want to talk to you about what does that mean? Why should we care about 2 degrees? Remember, winter to summer, the temperature changes by 20, 30 degrees. We can cope at 2 degrees, right? So I want to talk about that. So that is the committed warming. That blanket is already thick to heat the planet, okay? So let me give you my forecast. I'm thinking about 30 years from now, TERI University will organize a similar lecture series. I won't be alive, somebody else. And some of you may be giving the lecture, and I'm hoping you'll say, yes, I heard Professor Ramanathan say it's going to warm. Okay, and you'll be able to test what I'm saying. So I said we have already dumped enough gases to warm the planet 2.5. Even if you reduce carbon dioxide by 50%, the warming will still be larger than 2.5. That looks outrageous, and I want to talk to you why that is so. And the other thing, this is the key. This is where our TERI University hope will organize a meeting 37 years from now to test my prediction. We will very likely reach 2-degree warming by 2050. This, when I published, people were skeptical. Now many modeling groups have come to the same conclusion. The only way to avoid catastrophic warming in the long term is reduce CO2 emissions, starting from now. There's no question. But on the other hand, if we focus on the near term, if you're selfish, I'm going to worry about my lifetime, then you can delay the 2-degree warming by at least 3 to 4 decades if we reduce 4 warming pollutants, not CO2, methane, ozone, HFCs, and black carbon. I'm going to talk to you about that. So this is going to be my next couple of lectures. So keep this in mind, okay? The key thing is there is a so-called goalpost. Everyone says 2 degrees, dangerous climate change, we should avoid reaching that. They thought it's coming 2100. My work says, no, it's just around the corner, okay? So going back to this now, the first question you can ask me, maybe you can do it in a discussion session. Wait a minute, he told us we already dumped enough gases to heat the planet by 2.5. We have not seen that. The planet has warmed only by 1/3 of it, 0.8 degrees. What has happened is now I need to make that blanket a little bit messy. Okay? Remember, I don't have to talk to your Delhi aides about the haze. You see this pollution layer, right? The fact that you're seeing it means it's reflecting sunlight. So it has reflected enough sunlight back, but this is happening around the planet. So it has acted like a mask. Okay? That's a Venetian mask. So you really have not seen the full nature of this beast. It will act like mirrors. And you can easily say it when you fly up. Just as you clear about 2 kilometers, look at the horizon, you will see a dense haze everywhere in the planet. I have pictures of this on my website. So that's mirrors on the blanket. By sheer dumb luck, as we are dumping these heat-trapping gases, we also put mirrors on the blanket, which have prevented us from seeing the true nature of the greenhouse beast. And IPCC estimates it has masked about 50% of the warming. Okay? The third thing is that, unfortunately, when we put the mirrors, we also put a dark substance called black carbon. You all know what it is. You know, you see a dark smoke coming out of diesel, or when you fire burning. So think of that black carbon as a smoke in your blanket. Okay? It's trapping sunlight. It's not trapping infrared, but it's trapping the sunlight and heating the blanket directly. So those are the three things you have to keep track of. What we have done is given you a thicker blanket, and we put some mirrors on it, and we also put some smoke on it. Okay, so those are the three we have to deal with. So what is that? Aerosols, this blanket business. That's a picture as I was landing in Los Angeles. I had a hard time talking to people about this. It was too complicated. So I had to use visuals. You see this brownish layer over, it's called brown clouds. It's Los Angeles. The brownish color comes from black carbon. You remove the black carbon, it looks whitish. That's the mirrors. So tiny amount of black carbon is hiding this mirrors. So I think I'm getting late behind. I'm going to skip this. So far I made everything look like we understand the system perfectly. There is one thing we don't understand. That is the source of the biggest uncertainty. If I spend sleepless nights, it's because of this, which is that we don't know is warmer planet would be more cloudy or less cloudy, particularly more low clouds. Because the low clouds, remember I told you the albedo is 25%, 28%. 28% is reflected to space. Only 13%, 13 of the 28 comes from scattering by ice sheets, atmosphere. The remaining 15 is from clouds. And you know that, right? When you fly over clouds, it looks white. They are the biggest mirrors we have. If those clouds disappear with a warmer planet, you will let in more sunlight, amplify much more than what I'm telling you. On the other hand, with a warmer planet, you are evaporating more moisture, you can build more clouds, and it can protect us. So it depends on if nature is going to be benevolent or decide to punish us. Okay? And we don't know the answer to that. That is one of the biggest uncertainty in all our predictions of climate change. So that is why it was very important for me to say our prediction we made in 1980, the warming was there. Okay? So, but when you talk about uncertainties, those of you have to remember, you're going to be asked, if you persevere by my lectures and you start taking policy actions, the first thing they're going to say, oh, this field is so uncertain. My answer to that is uncertainties can go both ways. It can make the problem less or more. Okay? So what do we do as prudent citizens? This I'm going away from science. You pray for less, but plan for more. Right? I honestly, without any joke or humor, I don't pray much. If I pray, it is that I hope the skeptics are right. There is something we have left out. And the climate change is not going to... I think that's the best hope we have now. Because we are not taking any actions. So why this 2 degrees is such a big deal? If you look at the temperature of the past, I'm just going to leave the last one here, the tectonic time scale. This we know, the last 3 million years, there is a regular beating. We go from cold, ice age, to warm. Warm to cold, cold to warm, about 100,000 years frequency. Okay? It's regular, at least over the last 5-6 cycles. And then you go to the last 50,000 years, we were subject to one of the biggest ice ages about 15,000 years ago, you can see here. And then it moved out of it. We are in what's called an interglacial. the last 6,000 years, we have enjoyed a stable climate. There are many who are seen to suggest that's what permitted civilization to develop now. Okay? Stable climate. I'm having a problem with this. Yeah. The problem with the global warming is we are going from here to here. See, if we had been here, coal, global warming would not be a problem. We would in fact welcome it. But we are here, the warmest, and we are trying to push it there. And unfortunately, if it goes beyond 2 degrees, we don't have any analogs to see how the planet would look like. That is the problem. We don't have instrumental data to say, well, 2-degree planet is going to look like this, so this country has to worry about this country doesn't have to. We don't know. We are just left trusting our models for that. That is the crux of the problem in my mind. Okay? So I want to conclude this with one last point. Again on the science. After hearing all of this, you can still say, well, it was nice, sort of persuasive, but I still don't believe it. Okay? So I want to say, I studied in India. I did my undergraduate degree in Annamalai University in engineering. Then I did my graduate work, a little bit, a master's, designing instruments. When I went to the US, my work was studying planets, climate of Mars and Venus. And if you look at our neighbor, Venus, it's the brightest object in the sky. Why is that? It's covered with clouds, 100% cloudiness. So if you believe this albedo effect, you would say, oh, Venus should be cold because it reflected 70% of the sunlight. But it is the hottest of the inner planets. You know that, right? Its temperature is about 700 degrees Kelvin compared to Earth, which is 288, about 3 times. I mean, huge. Global warming, I'm talking about 2 degrees. This is 400 degrees warmer. So the explanation you would get in your high school or undergraduate, even graduate, why is Venus hot? Oh, Venus is close to sun. It's nothing to do with the gases, it's the sun which is heating it. Look at the sunlight coming in. It's almost twice as much as Earth, so it looks convincing. But then when you figure out how much it is reflected back, the actual sunlight hitting Venus is only 200. Even less than Earth, because Venus has bounced everything. It's got these huge mirrors. So what's the explanation you have? Venus has the atmosphere is entirely carbon dioxide. So it is the carbon dioxide greenhouse effect thrown in with other things, exotic things, which is what keeping Venus hot. So it's a greenhouse effect runaway. So the greenhouse effect is not a myth. It is well proven, well tested hypothesis. So with that, I conclude my lecture on science of climate change. In the lecture 2, I'm going to talk about impacts. The issues I'm going to address is why should we care about global warming and what are its impacts. I'm going to focus on the impacts on South Asia. We'll give you a global perspective. We'll quickly move into what's happening in this region. Okay? Thank you.